and has worked for Belimo since 2010. And before that, he was in Switzerland, project manager at other companies. He holds a diploma in mechanical engineering and marketing management. Thank you.
Okay, one more presentation to go, then it will be lunchtime. Mr. President, dear audience, thank you very much for the honor and the opportunity to present you trends and development regarding valves, the way valves are controlled, and the valves will be operated probably in the future. Energy efficiency, savings, these are the big topics in our industry, or let's say the last 15 years anyway. And with looking at energy savings and all this new stuff, we find also new problems. One might be low delta T. Low delta T is an issue, as Jim described already this morning, that occurs in even the best plants. But mainly it is addressed to the big things like chillers, the networks, no matter if this is district cooling or district heating. But there are also the little things that cause problems. The many, many little things that are integrated in our projects. I refer to valves. There are 1,500 until 2,000 valves in one building, and they have a significant impact. They really cause trouble. Because we are facing a permanent change when we operate our systems. There is a change in the customer requirement, in the comfort requirement. There is a change in the flow inside of the pipes, the pressure. There are changes in the temperature, no matter if this is the temperature in the water or the supplied air temperature. So, on the other hand, we also have to consider the changes in our equipment, because there is an aging taking place. There's a degradation, and also there are some design changes. And this brings me to the question, do we really know what's happening in our systems? Are they transparent? This is in brief what will be the subject of my presentation. I will talk about, first of all, 3 different ways on how to control hydraulic systems. The traditional approach, pressure-dependent valve, what you all know. The momentary state, what can be addressed to pressure-independent valves. And let's call it the state of the art, what's now on the market available. These are modern 2-way valve concepts. These will be pressure and temperature independent valves. Up to now, we only talk about the PI, pressure independent valves. But there will be the question, is this enough just to take care of the pressure? Or do we have to focus even more on temperature? Power control. With our valves, we control actually the flow, the position. Or what do we do with this? I will show you what power control means. Delta T management will be a big part of my presentation. Delta T management might or will be one of the solutions on how to deal with low delta T. I will come to this in a further slide. And again, transparency. Transparency, transparency. How can we get this? At the end, I will show you also some projects that were realized with this new valve technology. Hydraulic control. Probably you will all know modulating valve, ordinary valve. Schematic looks like this. When we give a modulating signal, 0 volt, to simplify it, I say 0 volt, not 2 or 0.5 volts. 0 volt means valve is closed, 5 volts, the valve is half open, 10 volts, the valve will be fully open. This is the most simple and the most traditional way to approach. The control signals will indicate only a position. 5 volt means if you have a stem traveling of 5 centimeters, it will reach half of it. Nothing else. Because all the rest must be calculated. Let's say 15 years ago, the industry introduced pressure-independent valves. Have become very popular, especially for buildings like hotels, where you can duplicate and replicate a system. Let's say you have these here in this hotel, you will have 300 rooms, same fan coil, same size of the pipes, so you can use more or less a simplified version of a hydraulic system by using pressure-independent valves. There are plenty on the market. Flow control means I do not longer ask just for the position of my valve, I ask for the flow. Using a pressure-independent valve means 5 volts is always connected to, let's say, 50 liters per minute. 10 volts will always be 120 liters per minute. So it's always connected to flow. Position control just to the position we're traveling. What actually is our target when we think of valves? We want to transfer a certain amount of energy into this room. So, actually we know how many kW are necessary here in this room. So, why not set up a valve? But we don't say go for the length of a traveling path or a flow, but 10 volts equal 1000 kW. 7 volts accordingly will be 700. This is a new approach to valves now. To make it a little bit clearer, pressure-dependent valves, the ordinary ones, have a control signal and I open my valve. I have to do a lot of calculations, I have to consider the KVS, I have to consider pressure changes to get together with a custom supplier-specific characteristic curve, a certain power output, which again will depend on the A value meets the output in the performance of my fan coil. So there are a lot of uncertain issues in this, but this is the traditional approach. The power output here will be influenced by the pressure in the pipes, because these valves are pressure dependent. Doesn't mean you give 5 volts and you press actually 50 liters that you will always get these 50 liters. When the pressure is changing all the time, the flow will also be something totally different. And of course, when the flow changes all the time, we have totally different energy which is transported to the room. The coil characteristic must be taken into consideration. Not only the curve of the performance of this coil, but also what happens actually about the months and about the operation time that we have there. Temperatures are absolutely not taken into account here. This will look like this. If this is a hotel and you just use normal valves, there will be an area, this is for heating, sorry, not just for cooling, what we required here. Very close located devices will get a lot of energy through the water. Very distant ones will suffer. They will just get nothing, because the water usually will take the way of least resistance. So it will just more or less enter here and feed these two rooms. Of course, there is a possibility what you can do. You can use balancing valves. That means you have to open the pipe, you have to install it, you have to commission it. But to be honest, talking about balancing, I just read an article in Germany. They reckon that around 93% of all installations are not properly balanced. So when Germany has already this problem, how will be the rest of the world? I don't want to blame somebody, don't get me wrong. But there is a relief. Introduce pressure-independent valves. The good thing with them is they have a mechanism inside. Normally it's a diaphragm or it's just a resistance which should limit the flow. They would operate in a certain pressure level. Standard in the industry will be something between 15 to 400 kilopascal. And what you can do now, this is our same hotel. You just install these valves and they will adjust the flow in this pressure range. So between 15 and 400 kilopascal, once you say 5 volts, give me 50 liters, the valve will give you these 50 liters. All you have to make sure here is that the most remote installation has enough pressure. In our case, give this one 15 kilopascal, all the rest will work. That's a big benefit of these valves. Now it makes no difference if this is a constant speed pump or a variable speed pump. If this goes up and down, it will work. There are two kinds of valves. I will start with the normal one. This one is the symbol for just a control valve. And this is a pressure regulator, just like you know from the double regulating valves. This is the combination of something. This has been introduced 20 years ago in the market. And now has become more or less the standard. Here, you don't have to go through the control signal valve opening, but you refer immediately control signal to flow rate. And from there, the next step to the power output is quite simple one. Good thing, you can just skip all the pressure issues. The pressure can go up and down, so they will not care for any areas being closed down, any pumps going up and down again. It will just work and will maintain this pressure independent. So this is the mechanical thing. That's what you're going to find normally in DN sizes 10 up to 15, I would say. Because then the regulator would become too big. Everything stays the same, just the technology of the valve is a little bit a different one. Here, you have also a control valve, more or less an ordinary one. But here, this should indicate it's a flow meter. And what you need as well is some intelligence. Now, this is the point where smartness, as the mechanical pressure independent valves have, has to change to intelligence. So you need an actuation which gives you, or has a possibility to react on several inputs from outside. These ones, the electric pressure independent valves, will also refer control signal equals flow. With these ones, usually you have also the possibility to change the flow. That means 10 volts should not be just 100 liters. It might also be 93 or 125. You can set this with parameters normally. So the valve will know exactly what the output should be. The water is flowing from this side. I measure my real flow, what is going on. I know this is, let's say, 93. My valve should actually bring just 75, as an example. So the valve will immediately know, the flow is too high. I have to reduce it. With the actuator, I close my control valve, and so I can maintain exactly the proper flow. So the main difference here is the fact that I measure and I know what is going through the valve. I definitely measure. It's important to know. Is everything solved now? I don't think so. There are still a lot of issues that cannot be covered just with these pressure-independent valves, even if they are smart. We cannot just rely if the coil is big enough. This is in a proper state. Has the design been correctly made? How about the temperature changes inside of the water? Is our chiller working in the proper range? Will the chiller always come with the right supply temperature? And one thing that is unfortunately still always very much neglected is the degradation. That goes fast. I spent a couple of years in Dubai and I could see on a rooftop within 2 months there is a layer of 5 centimeters on top of our cooling towers. So, and you have to do a permanent maintenance, a permanent caring for this. How will you get the idea of this? The next evolution step to our valves, where we consider position control, flow control, will now be power control. Instead of going for a length or a flow, go directly to the power. The designer actually should know. He should have told us how much kilowatt are required here in this room. So there should be the possibility to say to a valve, when you get a 10-volt signal, supply energy or supply power. 10 volt means 1400 kW. And you can modulate on this line just like you would do with an ordinary valve. Just modulate. So once you have the flow and you have the temperature, then you know it all. Just have to have the intelligence somewhere built in where you can get the time and then you can do all the calculations. So, to resume. Simple and stupid valve, you need at least three steps to get the power into your room. There are a lot of influencing issues. With the pressure-independent valve, you refer immediately a control signal to a flow. That means you can skip caring of the pressure changes. Once you could go straight away to power control, you can cover now all these temperature issues and also the problems that you might have with your air handler or with your fan coil. What would be an application for this? Low delta T, as Jim addressed this morning, a big issue. I Googled and I found in half of a second 1.5 million articles mentioned there. So it is a big thing in our industry. Low delta T actually means the differential temperature, the difference between the supply temperature and the return temperature is lower than expected. And this leads to a lot of problems. Dubai, Middle East, the second biggest supplier of district cooling, is only able to sell 70% of its capacity because of the low delta T problems that are created in the not very well set up buildings, let me say it like this. But imagine, second biggest in Dubai, only 70% of the capacity can be sold. The rest, by the way, is charged to the tenants. So they try to get the money back from behind. But this is a thing that we need to work on. This is something that is critical. The causes of this low delta T, again and again, a too big pump, and not ideal circuit type. I don't know what kind of hydraulic circuits are preferred here in Cyprus, but in terms of energy efficiency, I would recommend to think twice if you want to continue to use these diverting circuits. The reason is a quite simple one. Once you close, or once you lock out this device at the end, all the water will flow more or less unused with one temperature level right back to the return. It comes here with 6 degrees, enters here, and goes back with 6 degrees. Delta T stays extremely low. A poor valve authority, changing of the pressures, a too big difference between valve closed and valve open. Missing hydraulic balancing, as I mentioned before, with Germany. What I saw quite often is also the design change. Sometimes the room will be just put into, let's say, divided by 2, and nothing is working anymore the way it actually was expected to be. Quite degradation. Watch what's happening on your rooftop. Watch what's happening inside your pipes. In Spain, a project could just provide around 42% of the flow because the pipes were so much clogged. A big company. Well, how did we come, or how was this new valve technology created? How did this come alive? MIT, Massachusetts Institute of Technology, probably everybody knows here. We do a lot of research together with them, researching any kind of issues. Besides this research project, there were talks, and they mentioned to us they faced a huge problem. It's a distribution problem on their campus. A campus that has been established, let's say, 20 years ago, and which has been growing. Now nothing was in tune anymore. So they asked us, together with them, to develop a system how energy transfer could be controlled much better from the plant. They have a central plant as well, to the respective places where the energy is needed. Well, we started with a quite simple thing. We start, what's the industry standard currently? Industry standard will be to use this setup, a control valve with an actuator, energy counter, balancing valve. Yeah, that was the start. And then we found this is not enough because you have to put some more things inside. It is a good thing to start with, this concept, but what was very much missing is intelligence. With the normal setup here, you have components normally from different suppliers. You have to select, you have to pick together, you have to look if the thing is matching well together. The idea came, make one valve out of it. One valve, similar to the electronic pressure-independent one that I mentioned before. It comes with a flow meter. It comes with a more or less ordinary control valve. But then you have to add something, temperature measurement in the return and the supply. And if I measure my temperature in the supply and the return across my coil, this is delta T. Important was, of course, to make it intelligent. Because there now, when you want to have an individual station, you need to have some algorithms, you need to have several things, also that you can do some calculations. With flow measurement, temperature measurement, on both sides, the time, you can calculate what is used here in your fan coil, or even the entire energy consumption over a certain time. Intelligence is the thing. We have all the components. You have the flow meter, you have the temperature sensors, you have the valve. What you need now is the intelligence. What else would be important to have? The possibility to parameterize these valves, to say, to give it a specific flow amount. Let's say I need in winter time on this specific room 100 liters, but in summertime I would need much more. That means 130, 140. And I need the possibility to change this very easily. Monitoring is a big issue. Transparency, what I mentioned before. To have the chance to watch what is going on. Where is a huge consumption? Where is the delta T in my building? Inside this spot. Want to know all this, also very important. Data logging. Data logging to do the preventive maintenance schedule. A good value is if you have it more than 1 year, let's say 13 months, every 20 minutes, so that you can really see over the year what was going on. Communication to BMS. Modern valves should be able to communicate in an easy way to the BMS or a superior position. BACnet, Modbus, all these should be kind of standard. Come just with the valve. What is coming more and more is remote access. Either, if you have the VPN, through the internet, or what would be even better, go through a cloud with applications where you can definitely immediately point what you need to have. We live in the IoT times, and Internet of Things is coming. Whoever has been at the ISH 1 month ago in Frankfurt, almost every hydraulics booth had something mentioned with IoT, Internet of Things. This is coming. Easy to handle evaluation tool for this monitoring and long-term data logging things should also be available.
5 minutes.
Hold on? 5 minutes, okay. And delta T management. Delta T management, back to low delta T, is quite important. I will come to this in one of the next slides. When we do data record, you will get this kind of data. By the way, these are real data. This is the performance curve of my fan coil, of my air handler. This is the curve of the low delta T, of the delta T, sorry. What you can see here, the more flow I give, the bigger is the output of performance of my coil. However, on the other side, the more flow I have, the more my temperature delta will shrink. This is a physical thing, and you cannot deny this. But what you can see here as well, it's not a linear curve, the performance curve of my air handler. It's convex, and there is a point where it makes no sense to put more water in. There is no more output. The curve will not grow. The only thing that will even decline is my delta T. The same curve, just put into 2. This is the convex part. This is more or less the flat part where I don't have any increase in power. This area is called heat exchanger saturation. Here, I waste money, I waste energy. So, there is no increase in power output, the delta T will even be more reduced, and my pumping costs are going high, but it makes no sense. There is no more power going out of my fan coil if it comes to this. The only thing is my delta T will decrease even more. So what I have to do is I have to avoid that my delta T gets below a certain level. And this level is just at the saturation level. With a smart valve, you will be able to set this. You can tell a valve, don't allow a water flow when the differential temperature supply return of my coil is below a certain delta T. Let's say 10 Kelvin. Once there's actually from the BMS a signal, open the valve fully. The valve will react at that moment where it discovers that the delta T is below 10 degrees. And then it will just stop the valve opening, and it will even force the valve to close a little bit. What it actually leads to is a curve that looks like this. Here this is my delta T that I want to maintain. This is a set point that comes. Here my set point is rising. At that moment my valve will realize that at this point the delta T is too small. And then it will reduce the flow gently to just keep the delta T. We are focusing here on delta T. That this one can be maintained. A valve focusing on maintaining the desired delta T. Of course, this delta T can also be set through the parameters. Yep. This project could be realized, and I must confess, they were just at the edge of purchasing 2 new chillers, 1 new chiller, and this is included here. But nevertheless, 1.5 million of annual saving at this project. This is more than impressive. In Germany, similar situation. This is for heating, a huge hospital complex. Everything has been tried out. This new valve technology was the only way how they could solve their issues. Now it looks like this. This is one of 3 circuits. They even didn't tell us how much savings they made. They were so much ashamed, so they just said it worked well and we're going to continue to use this technology. Another one is University of Miami Hospital. This is a hospital where they do a lot of genetic research, and they needed a very well and accurate system. This technology also helped them a lot to just continue to work properly. even in Singapore, this technology worked well. Singapore has a problem with the humidity. It's on the tropical level, and dehumidification even worked extremely well by considering this technology. Mr. Chairman.
Thank you very much.
Thank you.